So on page 6, we're talking about instantaneous rate of change, and here we're kind of building off a little bit of the work that we did on the previous page. We're talking about what a tangent is. So through the secant activity and what we talked about on the previous page, we got the idea that if you have two distinct points on a curve, there's a line segment connecting those two distinct points. So I'll draw my arbitrary curve. Always arbitrary, always the same curve, which is, I suppose, the definition of not arbitrary. Completely incapable of drawing a vertical or horizontal line for some reason. Yeah, you see, it doesn't lock into place the way it used to. Alright, so arbitrary curve. That's my function f of x. And we could have two distinct points along this curve. Okay. Those two distinct points could be kind of floating out in space. Right? But what I can do when I connect those 2 points, I can figure out the slope, and that gives me a secant. Now, if that second point, I just kind of make a big old second point there. If that second point is moving closer and closer to the first one, then what's going to happen is the corresponding line, which I can do thusly, use the actual line draw tool there. So that second line, as it gets closer and closer, that second point, as it gets closer and closer, is going to start approaching, instead of being a secant line, it would start approaching being a tangent line. All right, specifically at that same point. All right, so again, that second coordinate is moving closer and closer, and so the secant line is becoming less and less of a secant and more of a tangent. All right, so tangent. All right, so that's what we're up against here. How can we come up with, and that's going to be the theme of a lot of the stuff that we do from here on out, how can we come up with a model or a function that represents the equation of a tangent line, or I'm sorry, the slope of a tangent, without having to really kind of go crazy with the analytics of it? You know, we don't want to do a ton of work to come up with these values. We want to have an efficient way of doing it. That's going to be the subject of a lot of our studies moving forward. All right, so we know one limit definition one definition involving the secant is the difference quotient. And we have two variations on that. So we got this guy, and then we have the alternate version of it. So I'm going to take them both and bring them on over to the next page. All right, one at a time. When I find the limit as h approaches 0, that h represented a horizontal distance between 2 points. If that horizontal distance approaches 0, then those 2 points are approaching becoming 1 point, which is really awkward phrasing, but it's basically saying they're merging into 1 point. All right, the second point is moving closer and closer. It's kind of coming back into, converging on the first point. Now, in the case of the alternate limit definition, we could say this one of two ways. we could say that B is approaching A. All right, because the location of B and the location of A would have to end up being eventually at the same place. So it's really just a question of, all right, well, which one's going where? Is B going to A or is A going to B? And the short answer to that is yes, meaning it could go either way. So when I did my little demonstration above, I was looking at the second point moving to the first point, right? But I could have easily said, well, I got a second coordinate. Let me go red for those keeping score at home. I got a coordinate over here that's moving ever closer to this coordinate. And what would that look like? You know, so in that regard, we'd be looking at a tangent line in this neighborhood. Just move this down over here. So when I move that tangent line over here, or I'm sorry, when I move that first point towards the second point on the right hand side, that secant line becomes more and more like a tangent line. All right, so on a function you could have infinitely many tangent lines. All right, so that's part of the exploration that we're going to be embarking on, or the journey, if you will. If you will, what? Who knows? So just want to make this look halfway decent. Number 3, it says find the instantaneous rate of change for any point at which f of x equals x cubed minus x exists. Well, this is a polynomial function. Polynomial functions are everywhere continuous, so it's going to exist everywhere. So if I could find an instantaneous rate of change for any point along this function, that would be great. That's the objective. But it's going to take a little doing. All right. First thing that we have to come up with is the answer to the question. Well, which formula should I use? The limit definition or the alternate limit definition? All right. Well, one thing to keep in mind is they didn't give us any points. It says find the instantaneous rate of change for any point. So well, actually, I'm kind of wrong in saying that. Not only did they give us points, they gave us all of them. All right. So we're not restricted to just a domain of, let's say, like on the previous page, 1 to 3. So they didn't give us an A and a B value. So that would kind of steer me away from the alternate limit definition and gear me towards the ordinary limit definition of a derivative. All right, so I'm going to write f of x plus h. Well, I'll rewrite f of x first, and then right below that f of x plus h. Those are the two main components of the limit definition. So f of x is x cubed minus x. Whenever you evaluate a function, all you're doing is replacing the variable in that function with whatever you're evaluating in terms of. So if I said f of 2, I replace every x value in a function with the number 2. If I say f of smiley face, I replace every x value in a function with a smiley face. All right, in this case, I'm saying f of x plus h, so I'm going to replace every variable in the function with an x plus h. All right, so instead of an x, it's like we're upgrading it to an x plus h. All right. Now, we are going to have to clean this up and do a little distributive property. X plus h cubed. I mean, you might remember when we were reviewing pre-calc concepts, that was part of Pascal's triangle. All right, so we can expand this out you know, I'll just kind of jot it down right here. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. All right. The third row of Pascal's triangle is the one that we'd want, because this is, each row corresponds to a power. Power of 0, power of 1, 2, and then finally power of 3. Right? I mean, it goes on infinitely, but I only need it to go out as far as a power of 3. So when I expand this, I'm writing it as 1, 3, 3, 1. The x term gets raised to the power, right, whatever the power is of the binomial. So x cubed, and then we decline the power from there. So decrease power of 2, power of 1, power of 0. And then we go the other way. So I have h also raised to the third power, but that's the end of the line, and we decrease that power as we work from right to left. Chuck in some positive signs, and then we clean it up a little bit. All right. And we also have that minus x plus h, so I might as well take care of that while we're here. Little distributive property. So minus x minus h. All right. So cleaning this up, I would have x cubed plus 3x squared h plus 3xh squared plus h cubed minus x minus h. All right, all of that, as alarming as that might seem, all of that is the f of x plus h part of this difference quotient. All right, so you could look at a glass half empty, half full. You know, the positive outlook on this is, okay, well, we got all the hard work done. And the other way is like, whoa, imagine how much worse this could be. If that were a power of 4, we'd be at this for like the rest of the day. Yeah, I mean, it's possible. I mean, you could get something kind of complicated, and you'd be at it for a while, but that's not really the point of all of this. The whole point of it is to get a sense of how the derivative, this concept of a limit definition of a derivative, works. All right. So now what we do is we pop all that information into our difference quotient. All right. So we're kind of back to this guy over here. I'm going to do a little shrinky dinky over here. Move some things around. I'm going to move the power stuff up here, and I'm going to move this over here. All right, so when I apply my limit definition, I'm taking my f of x plus h, which is all of this. So all of this stuff is the f of x plus h. Then I'm subtracting from that f of x. So I got all this stuff. Then from that, I'm subtracting off the f of x. And then I'm dividing that by h. All right, and I'm slapping a limit in front of the whole shabiggity bangity boom here. Alright, so when you perform the operations here, you can see following order of operations. Take care of parentheses, nothing going on there. We could distribute if we want, but we could also kind of look at it on the fly. We have an x cubed minus an x cubed, cancels out. Clean that up a little bit. We have a negative x minus a negative x, so negative x plus x cancels out to 0. All right, so we're looking at a limit as h approaches 0, so same limit, just we don't need all the elements of the numerator anymore, which is good news, because you had to figure at some point this is going to simplify a little bit, otherwise, you know, what are we doing? Yeah. And so this is what we're up against, but we're actually in the home stretch, because if you notice across the numerator there's a whole lot of h. So if we factor out an h and cancel it, then we'll be able to apply our limit and we'll be good to go. And so we don't want to go ahead and plug a 0 in for h right now before we factor out, because if we do that, then we're going to be up against it. We're going to have a 0 over 0, and that's going to be a problem. All right, so we pull out the h. We have 3x squared plus 3xh plus h squared minus 1. Again, the whole thing is over an h. The h's cancel. So now it's just the limit of this remaining expression, which gives me license to replace all my h's with zeros. All right, so when I do that, and I'll just kind of do it on the fly here, the only terms that we're left with is the 3x squared and the negative 1. All right, and so what this gives you is an equation together with the limit part of it creates an equation. But this in and of itself is an expression that represents the slope of the tangent line for all values of x. Slope of the tangent line for all values of x. So 3x squared minus 1 tells me that if I know what the x value is, I now know what the slope of the tangent line is at that point. All right? Which in turn means that I know what the instantaneous rate of change would be. All right? So, for example, if I knew that the x value is equal to 0, then I would know that the slope at 0 would be equal to negative 1. So, you know, something, you know, you just kind of test a value based off of your own perception, and you just kind of look at it. So here I would say x cubed minus x. All right. Now I want this to really just kind of simulate the idea of 0. So I'd pop this at 0, or as close to 0 as I can get. Not really working. So give up and just type it in. Alright, then my b value, that could be whatever, because I'm just going to use my slider to get it as close as I can. Alright, so I know that the secant separated by 0 and 3, for example, the secant has a slope of 8, but as I move that point, a second point, closer and closer to 0, you start thinking about what happens, you know, and in terms of the decimal, you can look at it. That as I get closer and closer, so I'm getting closer and closer, it does appear to be getting closer and closer to negative 1. All right, until it goes undefined. But if I replace my x here with a 0, that would just give me the negative 1 pretty cleanly. And instead of doing this for, like, let's say a follow-up question was, All right, well, what about when x is 10? What about x is equal to pi, x is equal to e, x is equal to negative 32? You know, maybe we don't want to use the graph. Maybe we just want to have a simple function that'll do all that stuff for us. This is that simple function. All right. So that's a pretty important topic. I mean, it's the driving force behind the concepts associated with derivatives, instantaneous rates of change, basically Calc 1, all the stuff that we're going to be covering in the remainder of the course. But this is the beginning of that. You know, so number 4 is kind of like pretty much the same thing, except they give you the x value, and then I ask you to write the equation of a tangent. Right? The benefit, or the thing that makes this problem a little bit easier, is the quality of the function. X squared plus, minus 4 is a lot easier to manage than x cubed minus x was. So, but you would follow along using the same general strategy. F of x equal to x squared minus 4, and then I would need f of x plus h, which is replacing each of my x values, in this case there's only one, with an x plus h. You could still use Pascal's triangle here, but I don't know that you need it as much as you would need it in the other, or would have needed it in the other case. So x squared plus 2xh plus h squared minus the 4 that was already there. Alright, so that's my f of x plus h. Now when I go to find the limit, as h approaches 0, it's all this stuff minus, I'll say all this stuff, even though it really isn't a lot of stuff, divided by all this stuff. No, it's just an h. And then when you clean it up, x squared minus x squared 0, negative 4 minus negative 4, negative 4 plus 4, also 0. And so we're looking at limit as h approaches 0 of 2xh plus h squared over h. Now you can kind of clean it up on the fly. That's going to become limit as h approaches 0 of 2x plus h. Now you can apply your limit, replacing your h with a 0. Simplify, and you get 2x. And again, this is the slope of the tangent for all x. Alright, all wonderful information, but we haven't answered the question fully. We did all the hard work though. So the rest is going to be more of the basic variety. It's like Algebra 1 style stuff. Alright, so first thing I would have to say is that, you know, we probably need some notation to help us distinguish a function from its derivative. Alright, so what we do is we use a prime symbol. So we'll say f prime of x is equal to 2x. That prime notation, that's the slope of the tangent line, also known as instantaneous rate of change, also known as derivative. All right, so all of those terms mean the same thing. So slope of the tangent line, instantaneous rate of change, derivative. All right, all denoted with a prime symbol. There's other notation for derivative, but that's the notation that we're going to use at least to start. All right, so then they're telling us to do this when x is equal to 1. All right, well, we can do that. So f prime of 1. So 2 times 1 is 2. That's the slope of the tangent when x is equal to 2. And by 2 I mean 1. So when x is equal to 1. All right, so now I have the slope. That's good news. Now I just need a coordinate to work with. They told us in the open there that it was x equals 1, but they said nothing about what the y value is. So if I'm going to write the equation of a line, I need the slope and I need a coordinate. So I also need f of 1, which would be the original function. So here's my original function. Replacing the x with a 1. So 1 squared minus 4 negative 3. So that's a point that we know is on the line. I'm sorry, on the curve. So let me make that look a little nicer. That's not much nicer. All right, so we know that there is a coordinate of 1 comma negative 3. So I have a slope and a point. Or I could say I have a point and a slope, which means I could use the point-slope form of a linear function. And so that'll kind of get us the rest of the way. And just resize a little bit. You just got to know what the appropriate model ought to be for a linear function. Typically we use y equals m times x minus x sub 1 plus y sub 1, where x sub 1 and y sub 1 are a point along the curve. All right, so, and m is your slope. Essentially, we're popping in for this, this, and this. So y would be equal to 2 times x minus 1 minus 3. And that is the equation of the tangent line. So the equation of the tangent line is what we just came up with. That's what they were asking us for, so it makes sense that we would come up with that. But we do, after all that work, want to make sure that we did it right. So we go back to our model here, give it a look, and say that we have x squared minus 4. All right. When x is equal to 1, so I'll put my a value of 1, move my b value ever closer to 1, just to kind of get an idea of what that slope ought to be. So when it gets closer and closer, you can see as I get closer and closer that my slope seems to be moving in on 2, so pretty confident about that. Then in terms of the line itself, well, we learn by doing, so let me type in y equals 2 times x minus 1 minus 3. And so the big question would be, as my b value gets closer and closer to the a value, does my blue line appear to be approaching that line that I just put in the equation for? And it does appear that once this second point arrives at that first point, that it's spot on, that is exactly at y equals 2 times x minus 1 minus 3. All right, so it's pretty solid verification of all that hard work, which is good news. All right. Now, the last thing on this page is talking about a normal to a curve. It seems like, oh, I guess we got another throw-in topic on the last problem. Just like when we thought we were done. Equation of the line perpendicular to the tangent of a curve at a given point. Essentially, it's the same concept. So what I'll do is I'll just kind of take you through this a little bit quicker, because essentially it's just what we did in number 4 is just one little tweak in the last step. So let's do f of x 9 minus 3x plus x squared, f of x plus h, replacing all of my x's with x plus h's. So 9 minus 3 times x plus h plus x plus h, the quantity squared. So 9 minus 3x minus 3h plus x squared plus 2xh plus h squared. Alright, so that would be my f of x plus h. I would then find the limit as h approaches 0 of all of this, it's all of this minus all of that divided by all of that, the same thing from the last problem. So all of this minus all of this. You'll know, it's a nice little checkpoint. You'll know that you're doing things the right way if you get a cancellation of your f of x in the next step. Alright, so the f of x that you're subtracting off, that should all completely cancel away. If it doesn't, you did something wrong. Alright, so the 9 minus the 9 goes to 0. Negative 3x minus the negative 3x, negative 3x plus 3x goes to 0. X squared minus x squared goes to 0. Alright, so cleaning it up. We're looking at limit as h approaches 0 of negative 3h plus 2xh plus h squared all over h, which in turn simplifies to the limit as h approaches 0 of negative 3 plus 2x plus h. Alright, that got right on top of the page number there, so I'm not overly thrilled about that. Let me just grab this stuff and shove it on over here. Which in turn, when I apply the limit, gives me a negative 3 plus 2x. So negative 3 plus 2x is what I would call f prime of x. That's my derivative. Now they're saying for us to determine the derivative, the normal, which is the line that's perpendicular to the tangent line at x equals 0. So I'd find f prime of 0, which is going to be negative 3. Then, since I need a coordinate, I go back to my original function, which is 9 minus 3x plus x squared. So, f of x, 9 minus 3x plus x squared. Just verify. When x is equal to 0, so f of 0, replace all your x's with zeros, it's just going to give you a 9, which gives you a coordinate at 0, 9. Now if I needed the tangent line, I would just do what I did above. I got my slope model, my point slope form. We would have the slope, which would be a negative 3, but if I want the slope of the normal line, right, that's going to be the negative reciprocal. right? Because perpendicular lines have slopes that are negative reciprocals to one another, right? So I have my x1, I have my y1, but instead of putting in a -3 for the slope, I'm going to put in a 1/3. So y is equal to 1/3 times x minus 0 plus 9. And you could leave it like that if you want. You could also clean it up and write or y equals 1/3 x plus 9. Either way would get the job done. All right. So if you want, when you go to check this one, you kind of eyeball it and say, all right, I'm looking at 9 minus 3x plus x squared. We want to pin this at 0. Alright, I want to move my second coordinate closer and closer to my first coordinate until it locks on. Alright, but if it gets too close, you lose the line. So just get it really close without it ever, matching up perfectly. And then my new line should look like it's roughly perpendicular to what we just plotted. 1/3 x plus 9. Right. So, it's kind of iffy. That doesn't really look overly perpendicular, but when you look at the scale, it kind of makes sense. I mean, I'm going 4 boxes for 20 on the y-axis, 4 boxes for 5 on the x-axis. Now, if I kind of space it out a little bit more, it might start to look a little bit, give it more of a square look. If I hit the home button, it'll lock it up as a square set of coordinates. All right, so now it looks a lot more perpendicular, but it also kind of looks a little cramped. So, but that's the idea. You want to have something that at least appears the part. It looks perpendicular rather than tangent. All right. So that was